A series RLC circuit as a frequency selector. So now this series RLC circuit is used as a frequency selector. At the beginning of the class, in the yesterday's class, I told you it is used for the resonance circuit, electrical resonance circuit is used to distinguish between the different frequencies. Therefore, this RLC circuit will be used as a frequency selector. That is, you want to select a particular frequency, then that particular frequency selection can be made using this resonance condition. It is just like your FM radio. So in case of an FM radio, you want to listen at a particular station. So that particular station will have a frequency of maybe 93.5, right? So that when you tune that circuit, RLC circuit, in such a way that when it becomes 93.5 hertz, then you can able to listen to music from that FM radio. So this resonance circuit will be most useful for this purpose like this. Any series RLC circuit passes all waves of a finite frequency at some extent, but it will offer lowest impedance at resonant frequency. The lowest impedance resonant frequency దగ్గర వస్తుంది కాబట్టి అక్కడ బోర్డ్ అనే వేవ్ it can allow it అనమాట. సో ఆ ఫ్రీక్వెన్సీ దగ్గర మాత్రం it can allow the one. So then a series RLC circuit possesses the frequency selectivity and the ability to discriminate among waves of different frequencies. The band of frequencies which passes quite readily through the circuit is called pass band or bandwidth of the circuit. Now we'll see how the bandwidth of the circuit is determined. Now this is the, if you look at the current graph, right, under resonance condition, see here, this is we call it as the bandwidth. This is we call it bandwidth. It's a range of frequencies from F1 to F2. The circuit will allow all the signals during this frequency ranges. So see here, the definition of the bandwidth here, it is given. It is arbitrarily considered to be a range of frequencies, for which the current is equal to or greater than 1 by root 2 times the current at resonance. So this current is 1 by root 2 times the current at resonance, that is I max. అంటే ఇక్కడ కరెంట్ 1/√2 అంటే 0.70. సో 0.70కి ఇక్కడ పాయింట్ వస్తుంది, ఈ పాయింట్ వస్తుంది. అంటే ఇక్కడ నుంచి ఈ లోపల ది కరెంట్ విల్ ఆల్వేస్ బి మోర్ దాన్ దిస్. ది కరెంట్ I is more than the Im/√2 during that region, and that band of frequencies we call it as bandwidth. So right. So now that can also be called as the half hour frequencies కూడా పిలవచ్చు. ఎందుకు half hour frequencies? What is the power at this frequency? If you look at that power expression, what is the power at this frequency? Power is equal to I² R కదండి. So I² R అంటే I is what here at this one is Im square by 2 into R. Therefore, what is that Im square R by 2? This, what is Im square R? This is the maximum power. P max is equal to Im square R. That is by 2 means half hour. Therefore, the power at this frequencies, will be Pm by 2. That is why these 2 points are called as half hour frequency points. So అది ఇందాక ఇప్పుడు నేను చెప్పింది అదే, right? Therefore, how do you find this bandwidth? So the bandwidth is the difference of these two frequencies, f2 minus f1. Now let us find out the expression for the bandwidth. The current at resonance is given by I is equal to V by R, right? And impedance at resonance is R only. So the current at half hour frequencies, that is f1 and f2, చెప్పాను కదా, పాయింట్ దగ్గర half hour frequency is 1/√2 times 1/√2 times the current at resonance, and which is given by I is equal to 1/√2 into V by R, where V by R is the, so since I is equal to Im by √2, so here Im we have defined it as V by R. Therefore, that you substitute it here, then you will get this. Then therefore, the impedance at half hour frequencies is 2 times √2 by R. Obviously, the impedance, if you find out, you will get the √2 by R. Therefore, the impedance expression is given by Z is equal to R square plus X square, where X is the net reactance. X is a net reactance. Right. So if you take the square of that, what we'll get here, it is squaring this equation, R square plus X square is equal to 2R square, you will get 2R square, you will get, and from that one X square is equal to R square, X is equal to R. So what we have here, and conclude here, it is at frequencies F1 and F2, the net reactance is equal to the resistance, that is X is equal to R. And net reactance and XL minus XC is equal to R at these two frequencies. These frequencies there, XL minus XC becomes R. Therefore, the phase angle at these frequencies will be 45 degrees, obviously. You find out the phase angle. Phase angle expression is tan inverse of XL minus XC by R. Since XL minus XC is equal to R, tan inverse of 1, that is equal to 45 degrees. Hence, the power factor is cos of 45 is nothing but 0.707. So at lower half hour frequencies, ante F1, total frequencies on F1, out F2. At lower half hour frequencies, ante before resonant, F1 ante it is before resonance. Before resonance, XC is greater than X1. That we know it. Before resonance, the series RLC circuit behaves like a capacitive reactance. So it is behaves like a capacitive reactance, and therefore XC is greater than XL. Just hello, class. Hence, the net reactance becomes Xc minus XL. So net reactance before resonance frequency must be Xc minus XL. What is Xc? Xc we have defined it as 1 by omega 1c, and the XL omega 1L. So if you equate that equal to R, then simplify that equation, then you will get the expression for the lower half power frequency in radians per second like this. And at upper half power frequencies, this is half power frequencies. That is at F2, XL is greater than XC. Hence, I can write the net reactance is equal to omega 2L minus 1 by omega 2C is equal to R. And if you simplify this one, taking simplification and all, you will get the expression for the omega 2 upper half power frequency in radians per second as like this. Therefore, bandwidth. So what is the expression for bandwidth? Bandwidth expression is given by F2 minus F1 or omega 2 minus omega 1. So now if you use this omega 2 minus omega 2 is already defined in here, and omega 1 is defined like this. ఇందులో మీరు చూస్తే ఇదంతా కామన్ రెండిట్లో కూడా ఇది కామన్ కాబట్టి both gets cancel each other, then you will get right R by L. This is sorry R by L. So the bandwidth expression in terms of radians is given by R by L, or in terms of hertz is given by R by 2 pi L. Then we have a quality factor. One more factor is quality factor. One more important term we need to discuss here is quality factor. The quality or quantity factor of a resonant circuit depends on the sharpness of the current variation in the frequency response. So smaller the value of resistance are compared to XL and XC, sharper will be the response. See, so the quality factor is defined as Q factor and so this Q factor is defined as Q factor is equal to omega not L by R, right? That is inductive reactance divided by the resistance. So inductive or capacitive reactance at resonance by resistance. That is, it is the ratio of reactance to the resistance is called as quality factor. So quality factor, we can define it like that, right? So, or in other words, we can also define it as the ratio of voltage across the inductor or capacitor at resonance to the supply voltage. So that in that way also we can define the quality factor, right? Therefore, the quality factor, Q factor, we either this or we can use this one. So what is VL? VL is equal to I into XL. So VL is equal to I into XL, where XL is nothing but omega naught into L, right? And V is equal to I into R at resonance. At resonance, V this is at resonance only. Therefore, your Q factor then becomes VL by V. VL by V and omega naught L I by IR. Then what will get I gets cancel each other. Then what we will get here it is omega naught L by R is a quality factor you have, right? And that we have defined here. See. Similarly, right, you can define the quality factor in this way also, right? Another definition of quality factor is 2 pi into maximum energy stored divided ratio of maximum energy stored to the energy dissipated per cycle. So the maximum energy stored in inductor at resonance is given by the expression. So we know the formula energy stored in an inductor is given by half Li square. But since the maximum energy stored at resonance is nothing but Im half L I square, I place lo Im square పెడతాం ఎందుకంటే at resonance the current is maximum కాబట్టి. So the power dissipated at resonance is given by P naught is equal to Im square R by 2, right? Therefore, the power dissipation per cycle is given by P naught by F naught, and that if you substitute here, right, these two, then you will get the expression for this, and the same expression you got for the quality factor. Then the other important definition we have here is selectivity. The ratio of bandwidth to resonance frequency is defined as the selectivity of the circuit, and this is given by bandwidth by F naught. Bandwidth we define it as F2 minus F1 by F naught, and F2 minus F1 is R by 2 pi L, and F naught is 1 by 2 pi root over L. And if you simplify this equation, you will get this expression like this. So this is the selectivity of the circuit. Now let us look at one example in this one. A coil with inductance and resistance of 1 millihenry, inductance of 1 millihenry and resistance of 2 ohms respectively is connected in series with a capacitor, and at 120 volts 5 kilohertz supply, that is frequency supplies, determine the value of capacitance that will cause the system to be in resonance. You want to calculate the resonance capacitor at resonance condition. That is, the resonant frequency is already given. So Fr or F naught is already given as 5 kilohertz, that is 5000 hertz. So we have an expression, we already derived an expression for the resonant frequency, which is given by 1 by 2 pi root over LC. So now in this case, Fr is known to us, L is already given, L is given as 1 millihenry, 1 into 10 to the power of minus 3 henries. Therefore, you can find out this C, right? If you have, after substituting these quantities, Fr and L, in this one, the capacitance, we will get it as 1.01 microfarads. Then take another example from the data of problem 1. Determine the current at resonant frequency. Maximum instantaneous energy stored in the magnetic field of the inductance at resonance frequency. So now at resonance, what is the impedance? The impedance of the circuit is equal to R, that we have discussed. Therefore, the current is equal to V by R. What is V here? V is equal to 120 angle 0 degrees by R is 2 ohms. 2 ohms in this one is R is given as. Therefore, the current at resonance is given by 60 amperes. Then the second bit here it is maximum instantaneous energy stored. So we have a formula for the energy store, and the maximum energy stored means half L I max square. Therefore, I max square అంటే దీన్ని మనం RMS లో రాసుకుంటే కనుక మనకి we have a relation between I max and RMS. I max is equal to root 2 I RMS. రైట్. ఇప్పుడు ఇక్కడ ఐమాక్స్ స్క్వేర్ కాబట్టి అప్పుడు ఇది అవుతుంది ఐమాక్స్ స్క్వేర్ చేస్తే దీన్ని స్క్వేర్ చేస్తే ఇది కూడా స్క్వేర్ అవుతుంది. దెన్ వాట్ విల్ గెట్ హియర్ ఇట్ ఈస్ 2 టైమ్స్ IRMS ఈజ్ ఈక్వల్ టు IM స్క్వేర్. సో అప్పుడు IM స్క్వేర్ బదులు ఇది తీసుకెళ్ళి ఇది సబ్స్టిట్యూట్ చేసాం అనుకోండి ఇక్కడ. దెన్ ఈ 2 R2 క్యాన్సిల్ అయ్యి దేర్ విల్ గెట్ L IRMS స్క్వేర్ అవుతుంది. దెన్ RMS స్క్వేర్ ఈజ్ ఆల్రెడీ గివెన్ హియర్ 60. Therefore, that you substitute here, then you will get 3.6 joules. Then take another look example. A series circuit has a resonant frequency of 150 kilohertz and bandwidth of 75 kilohertz. Determine the half power frequencies. Since the quality factor is given by 150 by 75, this is the quality factor, and it is 2 and it is less than 10. Therefore, the approximation of 1 of problem can be used, and the exact relationship is this is the bandwidth expression, and we may work in kilohertz also, right? Then take the another example. Determine the parameters of a series RLC circuit that will resonate at 10 kilohertz. That is, the resonant frequency of R is given as 10 kilohertz and have a bandwidth of 1 kilohertz. So bandwidth is given as 1 kilohertz and a power of 15.3 and a voltage of 200 volts generator operating at resonant frequency. Right. So what we have to find out is determine the parameters of series circuit. That is RLC. We have to find out. You have to find out R, L, and C. Let us find out that. Now here at resonance, VR is equal to voltage across the resistor is equal to applied voltage, and the applied voltage is given as 200 volts. So since the applied voltage is given as 200 volts, VR is equal to 200, and the power is given as 15.3, and the power is equal to I square R V square by R. Either use this. Now we have used that formula here. Power is given by 15.3 and V is 200 volts square by R. And from that one, if you find out the resistance of a series RLC circuit is given by 2.61 kilo ohms. Then the second bit here it is, you want to find out the other parameters L and C. So for that one, we have a formula for the quality factor. Quality factor is equal to resonant frequency by bandwidth. So resonant frequency is given as 10 kilohertz, yeah, and bandwidth is given as 1 kilohertz. So therefore, 10 by 1 will give you the quality factor as 10. Therefore, when the quality factor is 10, therefore it is already also defined in this way: 2 pi of L by R. The quality factor can also be defined as XL by R. So or XC by R. Therefore, if you substitute that here, XL is Q quality factor is 10 and F is 1 kilohertz and R already we have found out from this one, then you will get L. You will get L as 460 millihenries. Then finally, you have to find out the capacitance. So the resonant frequency expression is already we know. FR is equal to 1 by 2 pi root over LC, and where the resonant frequency here it is given as 1 kilohertz. This is wrong. 1 kilohertz. Right. Then L is already we have determined, and from that one, if you find the capacitance, then you will get the capacitance value of 610 picofarads. This